Okay, let us start the lecture. We were discussing zero simple semigroups and simple semigroups. So today we have following proposition. Proposition if M is a zero minimal ideal. Zero minimal means it is a minimum among all the non-zero ideals. It's minimal, okay? So minimal ideal within set of all non-zero ideals. उसको हमने already define किया था. If M is a zero minimal ideal, if M is a zero minimal ideal, if M is a zero minimal ideal, then either M square equal to zero, then either M square equal to zero, either M square equal to zero, or M is a zero simple semigroup. M is a zero. M is a zero simple semigroup. इसको हम ऐसे लिखते हैं zero. M is a zero simple semigroup. Proof. So suppose M is zero minimal ideal. Suppose M is zero minimal ideal. It's the zero minimal ideal. M is zero minimal ideal. Since this M square, it's a subset of M, and M square is also an ideal, but this M is minimal among all the non-zero ideals. So that means this M square या तो ये zero के बराबर होगा, because M is minimal non-zero. Okay? अब अगर ये zero के बराबर नहीं होगा, अब चूंकि ये minimal है non-zero और ये भी non-zero, then M square must be equal to M. So then either M square equals to zero or M square equal to M. So if M square is zero, then we have done. So we can assume that M square is equal to M. M square is equal to M. This implies M cube is also equal to M, because M cube is M square, which is equal to M. Now let's take a non-zero element in M, because M is a non-zero ideal. Since this M is not equal to zero, okay, let's write it like this. Since this M is not equal to zero, M not equal to zero, okay, not equal to zero. So choose A not equal to zero in M. You can choose non-zero element from M because it's not equal to zero. Then S1 it's obviously subset of M. Then S1 is subset of M, because this is the minimal ideal containing A and this is also an ideal containing A, so this must be a subset of it. And this A is there. Okay, A belongs to S1 and A belongs to S1 so that means S1 is a non-zero ideal contained in M. Therefore S1 must be equal to M, because M is a minimal non-zero ideal. So now let's see this. Now this MAM, it's obviously subset of S1 because this M is subset of S. Okay, and S1 it's equal to M, and that M is equal to M cube. M is equal to M cube, which is equal to M. This M is equal to S1 okay, M, and that's equal to MS1 A, then S1M. Okay, S1M. Since M is an ideal, that means MS1 is equal to M A, and S1M is again equal to M, because M is ideal. Okay, M is both left as right sided ideal. This is equal to M. So we started with MAM and ends with MAM. So that means this M square must be, that means M is 0. M is a zero simple semigroup. M is a zero simple semigroup, because it's actually from the previous proposition where you have shown that S is zero simple if and only if SAS is equal to S. Here MAM is equal to M, so this implies MAM is equal to M. This is equal to M. So therefore, by previous proposition, M is zero simple. M is zero simple. M zero simple आ गया. जो आपको प्रूव करना था, इधर M स्क्वायर इक्वल टू 0 और M इज इक्वल टू 0 सिंपल. तो जब भी आपके पास M जीरो मिनिमल आइडियल होगा, उस केस में M स्क्वायर या तो 0 होगा या M zero simple होगा. तो इन केस M square is not equal to 0, then M must be zero simple semigroup. तो ये आगे आप यूज करोगे मिनिमल आइडियल्स के लिए. और इसकी इंपॉर्टेंस सब सेमीग्रुप विदाउट जीरो में है. अगर S आपके पास होगा सेमीग्रुप विदाउट जीरो, अगर विद जीरो है तो देखिए अगर S होगा सेमीग्रुप विद जीरो, उस केस में जीरो हमेशा मिनिमल आइडियल होगा. नॉन जीरो तो नहीं होगा, बट इट्स अ मिनिमल आइडियल ऑलवेज. जीरो इज ऑलवेज अ मिनिमल आइडियल, और यू कैन से मिनिमम आइडियल. इट्स मिनिमम एज वेल एज मिनिमल इन दैट केस with respect to the inclusion order. So this zero ideal is always a minimal or a minimum ideal. Okay, in case S is semigroup it's 0. So now if S is a semigroup but minimal ideals may be more than one minimal ideals, but in case of a semigroup without zero, the minimum ideal जो होगा मिनिमल आइडियल. मिनिमम और मिनिमल में फर्क क्या है? मिनिमम मीन्स मतलब विथ रिस्पेक्ट टू इंक्लूजन ऑर्डर होता है वो. सपोज अगर मैं कहूँगा ना M मिनिमल है, तो तो इसका कोई अगर होगा यहाँ पर कोई आइडियल n, देन दिस n मस्ट बी इक्वल टू m। तो ये क्योंकि ये मिनिमल है, और मिनिमम का मतलब यह है कि इट्स कंटेन्ड इन एवरी आइडियल। इट्स कंटेन्ड, इसका मतलब मीनिंग लग रहा है किससे, बट इट्स डिफरेंट। मिनिमल का मतलब है कि अगर कोई आइडियल होगा विच इज कंटेन्ड इन m, देन n मस्ट बी इक्वल टू m। तो मिनिमम का मतलब ये है इट इज कंटेन्ड इन एवरी आइडियल। अगर मैं कहूँगा मिनिमम आइडियल, तो जीरो आइडियल जो है ना, जीरो आइडियल इट्स मिनिमम एज वेल एज मिनिमम, बिकॉज इट्स कंटेन्ड इन एवरी आइडियल, एंड इफ देयर इज एनी आइडियल m contained in 0, then this m must be equal to 0, because ideal at least contains the element 0. So this m must be equal to 0 in that case if m is subset of 0. Now next we have a following exercise for simple semigroups without 0, for semigroups without 0. Okay, if S is a semigroup without 0, exercise, if S is a semigroup without 0, okay, then S cannot have more than one minimal ideal. Then S cannot have more than one minimal ideal solution. So let m and n be two minimal ideals, be two minimal ideals of S. Then this Mn is also an ideal, is also, it's very easy to verify, is also an ideal of S, such that it's contained in both M and it's also contained in N. But this M is minimal and Mn is contained in M. It implies that Mn is equal to M. And now second, this N is also minimal, Mn is ideal, contained in N. This means that Mn is equal to N. So both M and N, they are equal to Mn, which implies that M is equal to N. So there is only one, at most one. अगर होगा तो एक ही होगा. Okay, definition. If S is a semigroup with having a unique minimal ideal, then that unique minimal ideal is called the kernel of S. A unique minimal ideal, unique minimal ideal, okay, of a semigroup S, of a semigroup S is called a kernel of S, is called a kernel of S, okay, and is denoted by Ks. Now in case S is a semigroup with zero, then what's kernel? Kernel is a zero ideal, because this is the minimal. Then Ks is equal to, this is a unique minimal ideal. ओके, अगर यूनिक मिनिमल आइडियल होगा तो उस केस में तो ये है, Now next we have a proposition. Let S be a semigroup without 0. Let S be a semigroup without 0. If S has a kernel, अगर इसके पास यूनिक मिनिमल आइडियल होगा, if S has a kernel, अगर इसके पास kernel होगा, then this kernel K suppose, then this case, ये जो kernel होगा इसका, this is a simple semigroup. K is a simple semigroup. K is a simple semigroup. So it follows from actually previous proposition, since it's a minimal, unique, minimal ideal. So you can see that its square, K square, it is also an ideal. Yeah. So let's write on its proof better, or you can do it yourself also. It's not difficult. It's without 0. Okay, K square is not equal to 0, but K square is an ideal contained in K. So K square equal to K. Then you can see the previous theorem where you can obtain that K is equal to K for every element K, A of K, for every A of K. And from this you conclude that by applying the proposition 3.1.1, a semigroup without 0, इसकी proposition है, and you can see that from this proposition, what's the statement of that proposition? 3.1.1, a semigroup S is 0 simple. Okay, a semigroup S is 0 simple if and only if SAS is equal to S for all A not equal to 0. तो यहाँ पर आपके पास होगा S से K is equal to K for all A in K. So that means K is like 0 simple, but we don't have 0 simple here because S is without 0. So we can say it's actually simple in this case. So proof. For this actually you have to apply the corollary which you have obtained from the proposition 3.1.1 actually for a semigroup without 0. Okay, so you have to apply that proposition. A semigroup S is simple if and only if SAS equal to S. So वो proposition ये है, S is simple if and only if SAS is equal to S for all A in S. Okay, this is the criteria for a semigroup to be simple. Okay, SAS equal to S for all A in S. So let's write down the proof of this proposition. Okay, suppose K is a minimal, K is a kernel. Okay, K is a kernel, it's a unique minimal. Suppose K is a kernel of S. Suppose K is a kernel of S. Then this K square, it's contained in K, is an ideal of S. So therefore this K square, it must be equal to K, because K square cannot be equal to 0 because we have a semigroup without 0. S is a semigroup without 0, so K square is not equal to 0. That means K square must be equal to K, which gives K cube is equal to K. Then as in previous theorem, you can see that now as in previous theorem, okay, वहाँ से आप देखिए उसको, as in previous theorem, K is equal to K for all A in K. So now apply this result, this one जो मैंने यहाँ side में लिख दिया, SAS is equal to S for all A in S, means that S is simple. So that means K is a simple semigroup. K is a simple semigroup. K is a simple semigroup. Simple semigroup. Okay, finite semigroups can always have a kernel because आप एक डिसेंडिंग सीक्वेंस जो होगी ना वो ओब्वियसली किसी ना किसी जगह तो टर्मिनेट होगी, जहाँ पर वो टर्मिनेट होगी वही इसका कर्नल होगा, जो फाइनाइट सेमीग्रुप्स की बात में कर रहा हूँ. एक्सरसाइज ये आप खुद करो क्योंकि शो दैट एवरी फाइनाइट सेमीग्रुप हैज अ कर्नल. Show that every finite semigroup has a kernel. It's very simple. आप लीजिए सपोज S finite semigroup है, सपोज I इसका आइडियल है, ठीक है, I is contained in this strictly contained. अब अगर I ही मिनिमल होगा then it's the kernel. अगर I मिनिमल नहीं होगा तो इसका कोई सबसेट एग्जिस्ट होगा, से I2, okay, strictly contained here. Again, if I2 is not minimal, you cannot continue this process infinitely many times because our S is a finite semigroup. क्योंकि जब आप कहोगे ना I2 not contained in I1, इसका मतलब है कि I2 में कोई एलिमेंट ऐसा है जो कि I1 में नहीं है. इसी तरह ना I1 में कोई एलिमेंट है जो कि I2 में, यहाँ पर आपने लिखा I1 strictly contained in S, so यहाँ पर S में कोई एलिमेंट है A1 जो कि I1 में नहीं है. इसी तरह से I1 में कोई एलिमेंट होगा A2 जो कि I2 में नहीं होगा. तो अगर ये प्रोसेस ऐसी जाएगी infinitely many times, so you can have an infinite sequence A1, A2, they are all in S, but our S is actually finite, which is a contradiction. So that means this sequence must terminate at some stage, say at this stage ion. This ion, this will be the kernel of semigroup S. ये इसका kernel होगा. इसका प्रूफ आप असाइनमेंट सबमिट कीजिए. प्रूफ सोल्यूशन इसका, राइट, इट्स अ सोल्यूशन. Now the next proposition. If I, J are ideals of a semigroup S, if I, J are ideals of a semigroup S, such that I is contained in J, and there is no ideal B of S, and there is no ideal B of S such that I is subset of B subset of G. So सबसेट नोटेशन हमारे पास ये सिंपल है, तो इसको आप थ्रू आउट यूज कीजिए. सो I subset of B means either I equal to B or I is strictly contained, okay, means both. देन J ओवर I. अब क्योंकि I और J दोनों आइडियल्स है S के, तो इसका मतलब है I भी J का आइडियल होगा, I J का आइडियल है. सो वी कैन टॉक अबाउट द कोशेंट J ओवर I. दिस इज अ सेमीग्रुप J ओवर I. J ओवर I. दिस सेमीग्रुप is either zero simple or null. Is either zero simple it's zero simple or null, zero simple or null. Null means product of any two elements of j over I is equal to zero. j और I का जीरो एलिमेंट है, I खुद है, इसका ख्याल रखिए. तो आपने वो थ्योरम एक की, देयर इज वन वन कॉरेस्पॉन्डेंस बिटवीन द आइडियल्स ऑफ S, between the ideals of S which contains I and the ideals of J over I. नहीं, इनके दरमियान वन वन कॉरेस्पॉन्डेंस है. देयर इज अ वन वन, दैट्स द थ्योरम. अगर आपको उसका नंबर याद होगा, हम की है वो थ्योरम, उसका प्रूफ हमने नहीं लिखा, बट दैट्स वेरी सिंपल. यू कैन कंस्ट्रक्ट आइडियल्स लाइक दैट. सो प्रूफ मैं पहले मैं वही लिख दूंगा. So what's the statement of that? It's the proposition number 1.7.1 actually. You can see that proposition 1.7.1. So what's that? अगर I प्रॉपर आइडियल होगा S का और A होगा सेट ऑफ आइडियल्स S containing I and B with a set of ideals of S over I, then the map. So you can say there is a one-on correspondence. There is a one-one correspondence, means the bijection between. There is a one-one correspondence between there is a one-on correspondence between the ideals of J containing I. You can say there is a one-on correspondence between the ideals of J between the ideals of J containing I and ideals of J over I. आप इसका कोई भी आइडियल लीजिए ना, J और I का कोई भी आइडियल लीजिए, कोई आइडियल ऑफ J और I का लीजिए, वो इस फॉर्म का होगा, वो इस फॉर्म, ये भी इस फॉर्म का होगा, J1 over I, where J1 is ideal of J containing I. So there is one correspondence between the ideals of J containing I, J के आइडियल जो I को कंटेन करे, and the ideals of J और I. अगर J और I का कोई भी आइडियल लीजिए, वो आप इस टाइप का लोगे, मतलब you can find an ideal of J containing I. ओके. और कन्वर्सली अगर आप कोई आइडियल लोगे J और I के दरमियान, J और I के दरमियान आपको J by I जो है ना, ये कोशेंट, इसका आपको आइडियल मिले. ये आपने रिंग थ्योरी में अच्छी तरह से किया होगा ये रिजल्ट. इट्स वेरी सिंपल. और कंस्ट्रक्ट इस B को कैसे करें, इट्स वेरी सिंपल. इट्स अ सेट एक्चुअली, तो जिसको आपने कंस्ट्रक्ट करना है, बी आपको J और I का आइडियल लेना, वहाँ से आपको J डैश को कंस्ट्रक्ट करना है, और फिर आपको प्रूव करना है J डैश आइडियल है J का, जो कि I को कंटेन कर रहा है. सो वी विल यूज दिस एक्चुअली. So but we don't have any ideal between J and I. It's given that there is no any ideal between J and I. So that means we don't have any proper sub ideal of J over I. इसका कोई proper sub ideal नहीं होगा. So which means that J over I is actually zero simple. since there does not exists an ideal B of J such that I subset of B subset of J. So we don't have any such ideal, therefore there is no any proper subideal of J or I. So therefore this J or I is it's a zero minimal ideal. It is zero minimal ideal of S over I. S over I का ideal है ये, zero minimal ideal of S over I. So why it's a zero minimal? Because इसका प्रॉपर सब आइडियल नहीं होगा, इट्स जीरो मिनिमल है. अगर इसका कोई प्रॉपर सब आइडियल होता है ना, से ए इसका प्रॉपर सब आइडियल होता है, तो ए की फॉर्म क्या होती इज ऑफ दिस फॉर्म बी और आई, वेयर बी इज एन आइडियल ऑफ जे कंटेनिंग आई. ओके, बी जे का आइडियल है और कंटेन किसको कर रहा है, आई को. बट विच इज नॉट द केस बिकॉज वी डोंट हैव एनी सच आइडिया. ये एक्चुअली यही रिजल्ट आप यूज कर, जो मैंने ऊपर लिख दिया ना स्टेटमेंट, इसी का यूज आप कर रहे हो. So it's a zero minimal because it's the minimal among all the ideals, and it's also non-zero. It's not equal to zero because it's equal to zero only if j is equal to I. So that means j over I is zero minimal. Now you can apply that proposition. If m is a zero minimal ideal of S, then either m square equal to zero or m is zero simple. So therefore then now by proposition, let's write by proposition. मैं वही नंबर लूँगा जो यहाँ पर थ्योरम में है, इस बुक में है. by proposition 3.1.3 जो हमने अभी की 3.1.3, इसका j और I का जो स्क्वायर होगा, ओके, इट्स स्क्वायर, इसका स्क्वायर जो होगा वो इसके जीरो के बराबर, मतलब वो I के बराबर होगा क्योंकि I इसका जीरो है, वो I के बराबर होगा. और ये जो j ओवर I होगा इट इज जीरो सिंपल, it's a zero simple, is zero simple, zero simple. Okay, तो j और I square equal to zero, it means that j और I is null. That is j और, because इसका जो स्क्वायर है, if you take any two elements of j और I, उनका जो स्क्वायर आप लोगे वो हमेशा इस आइडियल के बराबर, वो हमेशा जीरो के बराबर होगा. I इसका जीरो है. So that is j और I is null semigroup, or j और I is zero simple, ये आपको प्रूव करना था. j और I is either null or zero simple. Next topic which is regarding J classes actually. So first we fix a notation. Let's fix this notation. For each A in S as a semigroup, for each A in S, write the principal ideal, principal two ideal, write the principal ideal S1A, S1, that's two-sided principal ideal जिसको हमने कहा था. This generated by the element A, generated by the element A by the element A, इसको हम कैसे लिखे, as J of A ब्रैकेट्स में. अगर मैं नीचे लिखूंगा ना ये J सबस्क्रिप्ट A, तो that means J class of A. तो brackets means it is the principal two-sided ideal generated by A. So that's this notation is we have S1A. S1 इसका मतलब है कि ये J है, this J. ये notation आप में फिक्स करनी है. अब इस पर हमें पार्शियल ऑर्डरिंग भी है ना, and we know that this J class of X is related to J class of Y if and only if the principal ideals are contained in J of X is subset of J of Y. तो ये तो हमने ऑलरेडी किया है ना, इस पर ऑर्डर जो कोशेंट्स पर कैसे हम ऑर्डर डिफाइन करते हैं. अब इस पर एक एक्सरसाइज हम करेंगे. exercise if J class of A, it's a class, okay, is minimal among the J classes, is minimal among the J classes, among the J classes, then show that this principal ideal, it's same as J class of A and it is equal to the kernel of S. It's a unique minimal ideal. It is a unique minimal ideal. Solution इसका, since this J is, it's a minimal among all the J classes, it's minimum among all J classes. So we first show that this is kernel, okay, this is the minimal, this is minimal, this one. It's given that J class of A is minimal, okay, among all J classes. So now we need to show that this J is also minimal, it's minimal.